Now let's assume that we have two waves that have different frequencies and they're going to interfere at the same position in space. And the wave function for the first wave is y1 is equal to a sine kx minus omega 1t, and the second one is a sine kx minus omega 2t. And we're looking at their interference at x is equal to 0. I have, using the superposition principle, the resultant wave function y1 plus y2 is equal to a sine minus omega 1t plus sine minus omega 2t. So this will give me minus a sine omega 1t plus sine omega 2t. Now, using the same trick, the thermodynamic identity we have used before, sine a plus sine b is equal to 2 sine a plus b over 2 cosine a minus b over 2. I can write for the resultant wave function minus 2a sine omega 1 plus omega 2 over 2t cosine omega 1 minus omega 2 over 2t. So you see at x is equal to 0, these wave functions are becoming y1 equals a sine minus omega 1t, and similarly y2 equals a sine minus omega 2t. But this minus sign is not important because it's a sinusoidal oscillation, so I can think of this in absolute value. So let's look at the absolute value of this oscillation. It's just a phase basically. So I can see that the wave function I have here in absolute value is 2a sine omega 1 plus omega 2 over 2t cosine omega 1 minus omega 2 over 2t. So I see that this is an oscillation that has a high frequency component. So this is high frequency component. This is a low frequency component. So if I plot these together, I would see the following for y of xt. So at t is equal to 0, cosine function gives me a 1. So I'm going to have an oscillation between these maxima, let's say. And so I start out with 1. I go to 0 and then to minus 1 to 0 plus 1 to 0 minus 1, etc. So this is actually an envelope function. So this is the low frequency component. So I find that this is the cosine part, the low frequency component. And then there is a high frequency component, which is the actual oscillation here that starts out from 0. So this is going to be a sine oscillation. So I'm going to have an oscillation like this. And also this envelope will apply here. So I have to correct that. So I'm going to have this envelope here for the sine function. So the sine oscillation will be inside this envelope. So I will have this oscillation inside this envelope, continuing like this, etc. So if one listens to this sound that is created by the interference in time of two waves with different frequencies, you will be detecting these maxima. So you would be hearing this one, this one, this one, this one, etc. So you would be hearing the maxima. And basically, the number of maxima one hears per second, the number of maxima one hears per second is called beat frequency. And let's find out what this beat frequency is. So you can see that in one full cycle of the cosine function here, so let me highlight that here. So I start out with this maximum, go to minimum, go back to 0 and maximum. You can see that in one cycle here, at the beginning of the cycle I have heard one beat, and here in the middle I have heard one beat, and then this is the point where the next cycle starts. So I hear 2 beats per cycle. So I have 2 beats per cycle. So what is the beat frequency then? So basically I have to look at when the cosine function becomes plus or minus 1. So it is cosine 2 pi f1 minus f2 over 2t is becoming plus or minus 1. So when does that happen? When t is equal to 0 here, and when t is equal to so this has to be pi 1 over f1 minus f2. So this is the first time I hear it. This is the second time I hear it. So I'm going to have in 1 second and the third time I hear it, that is the end of the period, t2 is at time 2 over f1 minus f2. So in one period we observe 2 maxima. So this is actually the period of the cycle. And so for the beat frequency, I will have beat frequency is equal to number of maxima I hear in one period, 2 over f1 minus f2. So this will be equal to f1 minus f2. Now f1 can be greater than f2 or less than f2. So I can say that the beat frequency is basically absolute value of f1 minus f2. So this is the beat frequency that I will hear. Now it turns out that the maximum beat frequency the human ear can detect is 20 beats per second. So let's put that as a side note here. We have a maximum beat frequency. So first of all, we have found beat frequency is absolute value of f1 minus f2, and maximum beat frequency the human ear can detect is 20 beats per second. So let's take a look at an example. two identical piano strings of length 0.75 meters are each tuned exactly to 440 Hz. The tension in one of the strings is then increased by 1%. If they are now struck, what is the beat frequency between the fundamentals of the two strings? Now I know that the propagation speed of sinusoidal waves on strings is given by square root t over mu. So, and the frequency is related to the propagation speed. V is equal to lambda 1 times f1. So f1 is v divided by lambda 1. So if I change the tension by a certain amount, I would be changing the fundamental frequency of that string. All right. So for strings in a piano, I have the following boundary condition: two fixed ends boundary condition, and the fundamental mode is the following. You have node, antinode, node, and lambda 1 over 2 is equal to L. Lambda 1 is 2L. So for your fundamental frequency, you would have V over 2L. So it's 1 over 2L square root T over mu. Okay, so the fundamental frequency is this, and then they are two identical strings. I'm changing the fundamental frequency in one of them so that it's going to become 1 over 2L square root 1.01 T divided by mu, because it's increased by 1%. Okay, and when they interfere, I'm going to have a beat frequency. Beat frequency is absolute value of f1 minus f1 prime. So this will be 1 over 2L square root mu square root 1.01 T minus square root T. So this will be the beat frequency. So I know what f1 is. F1 is 440 Hertz. Then what is going to be f1 prime? F1 prime will be square root 1.01 times f1. Why is that? Because if I take the ratio f1 prime over f1, I will get square root 1.01. So this is actually 1.005 f1. So this beat frequency that I will find will be 0.005 f1, the difference between the two, and that's going to be 0.005 times 440. That will be about 2 Hertz. So I cannot use this relationship here because I don't know what the length is. I don't know what the mass per unit length is. But I can, since I know what the fundamental frequency is to start out with, it's 440 Hertz. I can take the ratio and find out the change